So first of all, I want to thank the organizers very much for the invitation. The title of my talk is Dissipative Phases of a Bose-Einstein Condensate of Photons. So what I want to speak about, basically, first about I want to introduce our system, which is a Bose-Einstein condensate of photons generated in an optical microcavity. And then I want to talk about some dissipative phases, for example, a non-Hermitian phase transition. Okay, to begin with, let me show you this overview slide of coherent optical emitters. So this is the first talk on photon Bose-Einstein condensates. There have been talks about polariton condensates, where one operates in the regime of strong coupling between matter and light, and depending whether you have thermalization or not, we either have a polariton condensate or a polariton laser. So in the experiments I will be talking about, we are working in weak coupling between matter and light. So in non-equilibrium, one then, of course, has a usual laser, which is, a textbook source. There one has little or no thermalization, and photons leak out of the cavity before they have a chance to thermalize, or they would never thermalize. On the other hand, BC is defined to be in equilibrium. Experimentally, you at least want to be near thermal equilibrium. So you want the thermalization to be faster than photon loss. And what is interesting is that on this scale, old bulk semiconductor lasers, well, they're not in equilibrium, but on this scale, they would be more to the right-hand side of usual lasers. The reason is that to understand their spectra, one has to account for things like the Kennard-Stefanov relation between absorption and emission, which is a thermodynamic relation that I will be talking about later. And what I will talk about today is about physics that comes into play where one is not perfect in equilibrium, but there is some dissipation, and this gives rise to novel phases. And what relates perfectly to this conference is a proposal by Michael Wouters. I don't know whether he will mention his talk is tomorrow. He will mention it, as I understand, also. But so I will just briefly mention it as a teaser for that. So if one has in such a photon Bose-Einstein condensate dissipation, one can have vortices. These are quite unusual vortices. So there's not they're not stabilized by normal real interaction, but by nonlinear losses, and this can lead to a stabilization of vortices. First of all, regarding photon Bose-Einstein condensation, as my background, actually, historically speaking, is cold atoms. So if I think of a Bose-Einstein condensate, the first thing that comes into mind is a Bose-Einstein condensate of atoms. Here you see of time of flight images at different temperatures. And now the question is, what happens if you're trying to do the same experiment, just cooling down in 3 dimensions with photons? Now what happens is the following. The photons just go away. It's getting dark. The photons normally have no chemical potential, so they're not conserved particles. The black body radiation at 0 kelvins gives you the absence of photons, which is not a very interesting state of the light field. So how can you do better? There has been earlier work related towards photon Bose-Einstein condensation. The first work that I'm aware of is a proposal for photon BEC encompass scattering of thermal electron gas by Seldovich and Levich, 1969. So what they proposed is to scatter photons of electrons in thermal equilibrium in a plasma, and the proposal was that there should be a shockwave structure that resembles a BC. This was never observed experimentally. What does work experimentally, of course, are exciton polariton condensates, which are, well, you had talks on that already, which operate in strong coupling between matter and light in a semiconductor system. What is more close to the work that I will be talking about is a proposal for a photon fluid in a nonlinear resonator by Ray Chow. So what he wanted to do is thermalized photons by photon scattering, very similar to atom-atom scattering in atomic physics BEC experiments. So in vacuum, the cross-section for that, of course, is basically zero. So his idea was to enhance it by putting an atomic gas. The cross-section there is nevertheless too low to allow for thermalization, but I nevertheless think that this is a very nice proposal. Okay, so this is then the outline of my talk. I will first talk about our system. So what we do is we trap photons in a very thin wavelength-sized microcavity to change the dispersion relation from the usual linear to quadratic, that is matter-like, and we thermalize light by absorption and re-emission events on dye molecules. I will first talk about the thermodynamics of this system and then on observing Bose-Einstein condensation of the system. It's a two-dimensional photon gas, actually. I will then talk about experiments on a non-Hermitian phase transition, which is induced by losses in this system, by small losses in this system, and finally on a test of the fluctuation dissipation theory in the system. Okay, to begin with regarding our experimental scheme to create a thermalized two-dimensional photon gas. So, as I was mentioning, we use an optical microresonator, well, as it's also used in polariton experiments. In our case, it's a curved mirror microresonator, and the spacing between mirrors is very small. It's an integer times half the wavelengths, and for the sake of simplicity, let's set this integer number n equal to 1. Then it's very clear that very long wavelengths do not fit into this microresonator due to the boundary conditions on the mirror surfaces. We have a zero of the field here and a zero of the field here. There's a maximum of wavelength, so a minimum frequency of the light to fit inside. So we get a low frequency cutoff, similar as in a microwave waveguide, and this is for the TM00 mode of the n equal to 1 longitudinal mode manifold. And on top of that, it's higher transverse modes, and here at some point, the n equal to 2 longitudinal mode manifold sets in. And the dispersion relation then is not anymore linear, but we have this low frequency cutoff, and on top of that, the dispersion turns out to be quadratic. So next, we thermalize the light by putting dye molecules in liquid solution into this microcavity, and we thermalize by repeated absorption and re-emission events on these dye molecules, as I will explain in more detail in the next slides. So these are spectra of a typical dye molecules that we use, perylene, emit. You see here both the absorption and the fluorescence spectrum. There's a Stokes shift in between. And it turns out that if you divide the line shape of the fluorescence by the absorption, you get an exponential thermodynamic scaling. That's the so-called Kennard-Stefanov scaling, which is closely related to detailed balance. And this states, well, that's e to the minus h bar omega, the photon energy divided by kBt, the thermal energy. So if that is fulfilled, it turns out that after many absorption re-emission events, photons thermalize to this temperature T. And now the question is, well, one can show that quite easily that the asymptotic distribution is a Bose-Einstein distribution. But what's the background of this relation? Well, this is my simple model of a dye molecule with an electronic ground state and an electronically excited state. Now it turns out that collision from, we have very many collisions from solvent molecules with the dye, and correspondingly at a rate of 10 to the minus 14, 10 to the 14 per second, and that's of course much faster than the upper state spontaneous decay, which is perhaps on a nanosecond time scale. Correspondingly, we get a thermalized distribution, not just in the ground row vibrational manifold, but also in the electronic, in the row vibrational manifold of the electronically excited state. And if both the ground and the electronically excited states, row vibrational manifolds, are thermalized, this thermalization also imprints onto the spectra. And well, this is the background of this Kennard-Stefanov relation. Well, one can mathematically show that quite easily by summing up the absorption amplitude from these different sublevels and the emission amplitudes from the sublevels in the electronically excited state. And the temperature that comes into play there is the internal low vibrational temperature of the dye, which of course equals the kinetic temperature. In our case, this is at room temperature. Now, what happens if you absorb a high frequency photon before it relaxes to the ground state? It relaxes down to a lower low vibration level, and we get a Stokes shift. So in free space, after a few cycles, you run out of resonance and the thermalization stops. But in the microcavity, we have a low frequency cutoff, and we get a thermalized state on top of the low frequency cutoff. So that's in more detail how the photon thermalization in the microcavity works. So the longitudinal wave vector of the photons is fixed due to the low frequency cutoff. And by repeated absorption re-emission events on the dye molecules, we thermalize the two transversal modal degrees of the photon gas. So effectively, we couple our two-dimensional photon gas to the dye solution, which acts as a heat bath at room temperature. On this next slide, I want to convince you that the photon trapping in such a microcavity is formally quite analogous to the trapping of atoms in a cold atom experiment. Also, the numbers are completely different. Well, I already told you that we have a quadratic photon dispersion. Next, it turns out that we also have a trapping potential from the mirror curvature. The reason for that is if the photons move to the side of the system, due to the mirror curvature here on top, the spacing between mirror surfaces is smaller. So to fulfill the boundary conditions of the mirror surface, you need a smaller wavelength that is a higher photon frequency. Of course, in thermodynamic equilibriums, photons are not very happy with that, and they rather move in the center of the cavity. So what you do, you print a trapping potential to photons. So with that, the system becomes formally equivalent to two-dimensional gas of massive bosons, also with such an effective mass that's harmonically confined. And the energy is this effective mass times c square. Well, that's just writing the low frequency cutoff differently as an effective mass times c square. That's due to the frozen longitudinal motion of photons in the cavity. This next term is the kinetic energy of photons moving transversely in the resonator plane. And that's a quadratic term and in momentum. And this third term now is the trapping potential printed from mirror curvature, and for spherically curved mirrors, it turns out to be a parabolic trapping. Okay, for such a system in thermodynamic equilibrium, one expects Bose-Einstein condensation if the particle number is larger than a critical particle number, which is pi squared divided by 3 times kBt over h bar omega. Omega is the vibrational frequency squared. And if you put in numbers at room temperature, you arrive at 77,000, which is a reasonable number. So why is that you can expect to get a BC at room temperature, whereas dilute gases you have to cool to the nanokelvin regime? The reason is that the effective mass is very small. It's about 2 electron volts, the energy of a visible spectral range photons in mass units, where you arrive at several times 10 to the minus 36 kilograms, or 10 orders of magnitude smaller than the mass of the rubidium atom. Corresponding, the vibrational frequency is high, and we can make this ratio, kBt over h bar omega, to be a reasonable number, even at room temperature. So that's our experimental setup. This is a scheme of our dipole microcavity. The spacing between mirror surfaces is not lambda over 2, but 7 times lambda over 2, but that works as well. And we pump at 45 degrees with a laser in the green. So that's a photo of this cavity. So these are the mirror surfaces, and the green is where we pump, and these prisms are such that the pumping light can transmit through. So to operate the cavity, we reduce the spacing to about a micron or so, and we put a drop of liquid dye in between, and that holds by adhesion. And we analyze the light that leaks out of the microcavity, both spatially with a camera and spectrally with a spectrometer. So this is now typical experimental data, first in a regime much below the onset of a BEC, where we see a thermal photon cloud, and above we in addition see a peak at the center that we attribute to the BEC. So to analyze things more in detail, we look at spectra. So these are theory spectra here, up here, and these are experimental spectra, first in a regime much below the threshold to BEC. Well, here's the position of the low frequency cutoff, and to the left, it's larger wavelengths that is, smaller wavelengths that is higher photon energies. So we basically see Boltzmann cloud on top of the low frequency cutoff. And if we are in the quantum degenerate regime, we in addition see peak at the position of the cutoff that we attribute to the BEC, and the width of that is due to the finite resolution of our spectrometer. So this was in 2010, and there's more recent works at Imperial College from Rob Nyman at Utrecht, Twente, Jan Kleers has his own group now. Baruch Fischer has a photon BEC in a fiber, and these are experiments in a semiconductor microcavity. There's also a plasmonic Bose-Einstein condensate by Pavi. She uses dimolecules to thermalize. And there's more recent experiments, both at Imperial College and Wroclaw, very nice experiments, who demonstrate a photon BEC in the weak coupling regime in semiconductors. Also basically that's a relatively widely available systems, so there might be more experiments upcoming. It's basically also semiconductors fulfill this Boltzmann-like scaling between absorption and emission. It's not, in this community, it's not called Kennard-Stefanov, but Rosley-Shockley relation between absorption and emission, but it's the same thing. Okay, next it turns out that in this coupled dimicrocavity system, one has quite different fluctuation properties and can have a grand canonical BEC. Usual BECs one can understood very well in the microcanonical or in the canonical ensemble, where the particle number is fixed. There one has fluctuations against the thermal cloud, but they are only Poissonian, and the second order intensity correlation at 0 times is equal to 1. In a grand canonical system, this describes a situation where you have exchange with a reservoir, a particle exchange, and it turns out that we can have that, or we automatically have that more precisely, because I mean we absorb photons with our dimolecules, so we go to the right of this photochemical reactions and back again, and this you can understand as a coupling of system photons to a reservoir of dye excitations. And if this reservoir is a large with respect to the system, then it's a true grand canonical system. And okay, seems to work again. Hope that's how it stays. Also basically, right. In a grand canonical system, we have the fluctuations. That's a system of the photons are coupled to the reservoir of dye excitations, and that